Good morning, and thank you for joining us. Today's webinar is on ghost peaks, how to fix a haunting problem. This is going to be presented by Jake Rebholz, our VOC product line manager. We will be taking questions at the end of the webinar, so feel free to submit those throughout the presentation. Okay, go ahead, Jacob.
All right, thank you much. Welcome, everyone. Let's dive right in. So the outline of topics I'm going to cover today is first and foremost, what is a ghost peak? And from there, we'll move into how to identify ghost peaks and their sources. Then we'll discuss a little bit about how to correct various sources of contamination. And finally, we'll wrap things up with some discussion on how to prevent future hauntings, so to speak. So all kidding aside, ghost peaks can be a really troublesome issue, especially if they start to interrupt with your calibrations or if they start to affect your low-end sensitivity. So what is a ghost peak? Quite simply put, it's any peak that does not belong in your chromatogram. So here, for instance, on the left side chromatogram, this is simply a system blank. No injection made on this GC, and we see a nice sharp peak right here, which just so happens to be naphthalene. And that would be an example of carryover. Clearly stands out, it doesn't belong. In the middle example, we have some internal standard contamination, where we've run an internal standard, and we have a nice sharp peak over here like we expect, but then we also have a couple little guys hanging out over here that don't belong. These might be target compounds, they might not, they might interfere with your calibration, they may not. And then lastly, here on the right-hand side, we have an example of a full system carryover. So we have our internal and surrogate standards, and then we have all these little peaks down here. And so these are a high standard carrying over into the next blank, or potentially a high sample carrying over into what is essentially a non-detect sample and may give you a false positive. Okay. But not all contamination is that straightforward and that easily identifiable. There are several other types of contamination that we have to deal with, and that could be an elevated baseline or a foreign compound contributing to target peaks, and last but not least, tailing or splitting of our target compounds. So for instance, here's an example of several runs in a row where we had a nice clean system, we have a nice calm, quiet baseline, and then we had something happen to our system, and now our baseline is significantly elevated. There's also a lot of contamination in here. Now, maybe an elevated baseline doesn't cause issues, maybe it does. In this case, let's say, for instance, this peak right here is a target compound. Well, because our baseline is now elevated, the peak area we see is less than half of what could be there if we still had our nice, clean, low baseline. So it may affect our low-end sensitivity. Here would be an example of contribution to target peaks. So for instance, in this clean system, this would be the expected peak area or peak height that we would see for this compound. And when we have a contribution of contamination, whether that be carryover of that same target compound or a foreign compound that shares the target ion, we see a larger peak here. And so this can cause false positives. It can skew our calibration if it doesn't occur in every single sample, only in some samples, things like that. And then last but not least, tailing and splitting. So for instance, on the top one here, we see a nice big peak with a long, broad tail. But if we look at a different ion, we see that there's actually a couple compounds in here. And then similarly, with these in the lower chromatogram, we have these little splits before and after, or we have this little hump here on our tail. And do we include those in the integration, or do we not? Do these little splits, do they occur with every sample? If they don't occur in all cases, and you choose to include them, maybe that skews your results. Maybe you need to include them when they occur, and you don't when they don't. It makes integration tricky. And then similarly here with this larger peak, is this split or is it two peaks co-eluting? So is this a contamination issue, or is it an application issue with our method parameters? And then how would you integrate this? Would you simply cut it right at the valley there? Do you need some of that area over here where that tail would have been for the first compound in order to get an accurate calibration? So what can we do to clean that up? Okay. So when attempting to identify ghost peaks in your chromatogram, you want to start by visually inspecting the chromatogram. And it really helps to have an example of a clean chromatogram or an example of your chromatogram before you had problems. So if you notice you're starting to have issues with calibration, or your check standards are failing high or they're failing low, or you don't have the low-end sensitivity that you used to, it really helps to have a chromatogram from when the system behaved the way you expected, and then you can compare that to what you're currently seeing. And this can help identify in particular extra peaks or an elevated baseline that may have snuck up over time and you didn't notice, and then also tailing or split peaks. So a month ago, 6 months ago, a peak used to be nice and sharp, now it has a broad extended tail, or it used to be a single peak and now it's fragmented and split. And then also, as I've just mentioned, poor calibration results can sometimes tip you off that there might be issues going on, such as foreign compounds contributing to target peaks or carryover contributing to those target peaks and skewing results. Okay, so let's go over some troubleshooting tips before we get into how to actually identify the source of our contamination. First and foremost, take a few minutes to go through the manuals for all of your instruments. That's both your GC and any autosamplers that you're using. The manuals typically have recommendations on some of the most commonly contaminated systems and components, so to give you a good idea of maybe where to start, to walk you through how to do some of the most common maintenance tasks, such as inlet maintenance on a GC, or what the proper column depth will be on your GC and for your detector, to walk you through that sort of stuff. And then same with the autosampler, may discuss common procedures such as how to change a syringe or how to change an analytical trap in the case of purge and trap. Also, we want to make sure that we're looking at the facts that we have available to us and we're using valid reasoning. For instance, if you have multiple GC systems in your lab and you prepare one standard that you then use to calibrate all of those systems, if one of the systems has a contamination issue, it's likely not going to be the calibration standards because that didn't cause an issue in the other systems that look just fine. We could also rule out things like solvents or shared glassware or carrier gas in this similar fashion. So rather than spending half a day troubleshooting these shared components, use some common sense, look at your other systems, see that they're functioning the way you expect, and then know that you can rule those things out. Lastly, avoid quick fixes and don't take the shotgun approach. It's really important that we get to the core of the problem and really understand the root cause. Because if it turns out it's dirty glassware, which is caused by insufficient cleaning technique, that's something you can correct, and then you can move forward and not have that problem repeat. Or if it turns out that you have a bad batch of calibration standards, rather than continuing to use them and continuing to see issues, we can eliminate those standards, purchase new, and correct that issue. If we just throw 5 or 10 parts at it and the problem goes away, you may have replaced some really expensive components that didn't need to be replaced. And then the next time the issue comes back, you still don't have a good understanding of what caused it in the first place. You do the same thing again, you're throwing even more money down the drain. And so as with all of these, be patient. Work your way through it stepwise in a logical fashion and really get to that root. Okay. So the first thing we want to do when we're trying to find the source of our contamination is we want to break our system into the major components and then test each one of these individually. So for instance, on the GC, we could look at the GC inlet, the column, and the detector as 3 separate components. And then with the autosampler, depending on what style of autosampler you're using, we can likely break that down into some major components as well. And so as we talk about specific autosamplers later in this webinar, I'll mention some of those subcategories that we can break those out into. But before we move into actual troubleshooting techniques, I'd like to take a moment to talk about method parameters. Anytime you have an issue pop up that didn't used to be there, the very first thing you want to do is take a step back and ask yourself, have I changed anything in this system? So for instance, if you weren't happy with your GC cycle time and you wanted to try to shorten it, did you do something such as reduce the upper temperature or shorten the hold time at the end of the run that may have caused some issues? Or did you change out columns and forget to change the oven program to match the new column? And then with autosamplers, do you have a sufficient amount of rinses for a syringe system, for instance? Things like that. Look at those parameters and make sure that they make sense for what you're trying to do. And if all of the method parameters match up, then we know that we have some type of contamination in the system, and we can work to understand that. So a good example of method parameters, as I mentioned with GC cycle time, if you see your heavy compounds disappear off the end of your chromatogram, for instance, and then they show up in the following blank, what's likely happening is your column is not getting hot enough, or you're not maintaining that top temperature long enough to allow those compounds to sweep fully out of the trap and into the detector. So you'd want to increase your final temperature or your hold time to make sure all those compounds are swept through the detector before starting the next sample. Similarly, you could have compounds condensing in your inlet, and so if your inlet temperature isn't high enough, you might have things condensing out, and then you'll see some carryover or reduced sensitivity. And then the same holds true for any transfer lines from an autosampler to the GC. Okay, so if we've ruled out method parameters and we've ruled out any of the particular consumables and things that are shared with other systems that don't have issues, we want to start by running some system blanks. So first run a full system blank. That's with your autosampler, everything attached and in play, and then run a GC only blank. So remove the autosampler from the picture, rerun, and then lastly, look at the detector only if possible. And then compare those results. So if you see the contamination with the full system run, but not with the GC only, then you know that the issue is in the autosampler. If you see it with the full system run and the GC only, but not in the detector, then you know the issue lives somewhere in your GC. And then if you see the contamination in all three blanks, regardless of which component you remove, then you have something broader going on in the whole system. Okay, so let's say you only have one system and you can't just rule out your solvents or your standards based on the fact that it works in other GCs. How would we troubleshoot this? In the case of solvents, we're talking about methanol or acetone. Start with a direct injection of the solvent that you're using to prepare your standards. Do you see the contamination or not? And then compare those results to a second source if possible, or if not, compare it on a second GC system to confirm that the contamination either shows up in the second system or in the second solvent or doesn't. And then don't forget that the syringe you're using for that direct injection could actually be the source of contamination and not the methanol itself. If you've ruled out the solvent, then we want to look at our standards. Crack some new ampules, prep some standards, do direct injections of those standards. Do they look clean or do they not look clean? Do the same for your calibration standards, internal standards, and surrogates. And then, again, don't forget that your syringes could be your source of contamination, and so make sure you're using clean or new syringes to do this. Also, we could look at our carrier gas, and this would include our gas filters, the supply tubing, the regulators, and the carrier gas itself. One way we can troubleshoot this is allow the GC oven to sit at or below our starting temperature for a number of hours, up to a day or maybe even 2 days, and then run a GC blank. Follow that GC blank immediately after with another blank, and then do we see any difference in the peak area or height of that contamination? So if it's really large in the blank that was run when the system sat for a while, we know that that contamination is collecting on the GC column. And then the next blank doesn't have as much time for contamination to collect, and so there's less contamination. If the peaks are of similar size, and that points to some other portion of the system. So in this case, if it was coming from your carrier gas, start by checking your filter. Is it exhausted, or does it still have some capacity left? When in doubt, replace it. And then your gas supply. It could be the tank, it could be the tubing, or it could be the regulator. So set up a whole second system, separate tank, regulator, and copper tubing. If you don't see the problem, then you can work your way back and figure out where that issue is actually coming from in your carrier gas supply. Okay. So if the issue doesn't live in your solvents and it's not in your various shared consumables, then let's start with the detector and we'll work our way back through the chain. So in the case of mass spectrometers, check your tune reports. Is the detector working properly? Is it leak tight, or do you have a small leak? Do you have sufficient vacuum, or is your pump going bad? And is the source clean? Does it show signs of being contaminated, or does it need to be cleaned? So if you've cleaned your source, you verified it's leak tight, everything looks good from a physical standpoint, but you still have contamination, then we would have to move on to some other portion of the system. For other types of detectors, remove the column and cap the detector. And again, run that detector only blank, and then do you see issues? If it's improved and the contamination is coming from the GC or from the autosampler somewhere upstream, if it's the same, then it's likely coming from the makeup gas or the detector itself. Okay, so if we've ruled out the detector and presumably ruled out the autosampler based on our system blanks, then we're looking at the GC. And that gives us two components. We have the inlet and we have the column. So with the inlet, just do basic inlet maintenance. Replace the liner of the septum, clip the column, reinstall, make sure it's installed at the correct depth, and rerun your blank. If you still have issues, you could look at other sources such as the split ratio, verify that it's actually working properly, so measure the flow out of your split vent. If it's sticking or it's not opening correctly, it could be overloading the column, which is going to cause carryover. And then look at your septum purge. Is the septum purge working correctly? If not, you might have off-gassing from the septum making it onto the column, or you could have contaminants building up in that tubing for the septum purge and then backflowing back into the inlet and being carried in. If we've ruled out our inlet, we've done all of these maintenance checks and we still have issues, now we're looking at our column. So we've already clipped our column during inlet maintenance, so now would be the time to swap the column out completely. Put in a separate column of known performance or a brand new column, and then rerun your blanks. Do things look better? If they've improved, replace your column. If you still have the same issues, now we're moving on to some other portion of the system. Okay, so that brings us to autosamplers. I'm going to talk about three different types of autosamplers today. Liquid injection towers, Headspace Autosamplers, and then Purge and Trap concentrators. So if the issue is coming from our liquid injection autosampler, we really have three main sources that could be contaminated. It could be our syringe, in which case you'd want to replace the syringe or clean it, rerun, verify whether or not you see improvement. If it's not coming from the syringe, it's likely coming from the cleaning solvent. And again, this goes back to those method parameters. Verify that you have an adequate number of cleans for the samples that you happen to be running with this syringe. If it's not that, check to make sure that your solvent's not contaminated. So you want to make sure you have a clean, contamination-free rinse solvent for your system. And then it could also potentially be coming from your vials. So verify with some solvent in an empty vial. Run that. Does that vial look clean? Confirm with a vial from a different lot or a different manufacturer. Okay. So next, Headspace Autosamplers. We have a couple. Headspace Autosamplers are really pretty simple, so there's only a few things that really can contribute contamination to the system. Primarily, that would be the needle, the transfer line, the sample loop, the vials themselves, or the associated valving and tubing with the system. So the vials, again, verify that they're clean. Use vials from a different lot or a different manufacturer. Rerun. If you see improvement, that's your issue. If not, we want to look at the needle. This is most common source of contamination in Headspace Autosamplers tend to be the needle. So what you want to do is either clean that needle or replace the needle and then rerun. If you see improvement, you found your issue. If not, you would then move on to the transfer line or some other portion of the system. If it's a dynamic headspace, such as RHT3, then you'd want to look at the trap as well. So replace the trap, rerun, and verify that the system's been improved. Okay, so if it doesn't live in the vial or the needle, now we're moving on to the heated gas pathway of the system. So the transfer line, the valve oven, and the sample loop. Again, method parameters. Verify that your temperatures are sufficient to prevent condensation of your target compounds. Assuming all of your heated zones are set to correct levels and reaching those temperatures, then we're probably looking at some type of active site. And these tend to be persistent throughout the system. So often you're looking at cleaning or replacing the transfer line, the sample loop, and all valves and tubing associated with the valve oven, oftentimes. Okay, so purge and trap systems are a little more complicated because they're typically broken into two main components. We have the concentrator and its associated components, and then we have the autosampler and its associated components. But again, we can break these into two separate sections, and we can troubleshoot each one separately, and it makes a big job much easier to tackle. Okay, so looking at the concentrator itself, typically carryover is isolated to the late eluters, the heavy compounds, because they tend to not come off the trap very well, or they tend to condense out in cold spots and they hang around and then they show up in the next sample. But if it's contamination, like an active site or overloading of the trap, then it could be any or all compounds showing up. So we want to check and make sure that all of our temperatures are adequate throughout the system. So the heated zones are reaching the temperatures that are set and that those settings are high enough. And then we also want to pay particular attention on our desorb and our bake temperatures. So make sure that our desorb temperature is high enough to efficiently desorb the trap, and then make sure that we're actually baking it out and cleaning that trap between samples and not leaving anything behind in there. So if we've ruled out those method parameters, now we want to start our troubleshooting steps. And first and foremost, we want to do a desorb only. So we would just go into our software, step directly to desorb, run, and see what we get. If everything looks clean, then that's going to rule out our gas pathway right out of the gate, and then we know that we're looking at the liquid side of things. If we see the contamination, then change the trap and rerun. If you still see the contamination, then you're probably talking about an active site, and again, just like with the Headspace, you're looking at cleaning and or possibly replacing the transfer line, the 6-port valve, and any associated tubing. Okay. So next we want to disconnect, if our issue does live in our liquid side of things, we want to start by disconnecting our autosampler, and we want to disconnect or bypass all of those functions. So in this case, we would push a sample directly into the sparger and then run that. And so this is going to give us a look at our sparger, our sample introduction valve, and our drain valves. So with the sparger, if you see issues after running that blank, then check your sparger for discoloration. Or any other signs that it might have physical contamination in it. If you do see anything cleaner, replace that sparger and then rerun your blank and see if anything is improved. You'll also want to check your drain valve to make sure that it's functioning properly, or check your method parameters to make sure you're giving sufficient flow and time for that sample to drain. So if you're leaving just a little bit of standard left over in that sparger, and then you're not rinsing that out adequately, you're going to see some carryover. So just making sure that those parameters are correct as well. So if we've ruled out the concentrator as the source of our problem, now we're looking at our autosampler. And there's a couple things on the autosampler side in the liquid pathway that could cause issues. And it could simply be that it's not delivering hot water or the methanol rinse correctly, again tying into making sure that that sparger is clean between samples. But other sources of contamination could also be, again, the vials themselves, the multi-stage needle of the autosampler, the syringe or the sample loop, depending on the design of your system, and then any standard addition system that the autosampler has. So if you happen to have a combined autosampler that runs both in-vial purge soil samples and handles liquid samples, we want to start by figuring out, does the contamination live only in the soil mode or only in the water mode, or does it live in both? So run a blank for each mode to verify where the contamination shows up. If we only see it in the soil mode, then we're looking at potentially the needle, the soil valve, and the transfer line between the soil valve and the valve oven. If it only shows up in the water mode, then we're talking about the liquid handling pathway. So in that case, it might be the needle, the syringe, or the sample loop, and then the standard addition system. And if we see it in both, it could be the rinse water we're using, it could be coming from the syringe that's transporting that water, and it could be coming from the needle. Okay, so when talking about a syringe-based system, we want to start first by eliminating the needle by placing the transfer tubing directly into the vial of water and then having it pull from that source into the syringe. Excuse me. If this doesn't show the contamination, then we know it's the needle. If we still see the contamination, then clean or replace your syringe. If that doesn't fix the issue, then bypass your standard addition system next. If that fixes the issue, then you have an active site or a leaking valve or leak across a port in your standard addition system. And if you're still having issues, then you're likely looking at the multi-port valve on top of your syringe. In a loop and valve system, again, verify your loop rinse times, making sure that you're adequately rinsing the loop between samples, and then you're adequately draining that loop between samples. So again, if you're not giving enough time to transfer all of that volume out of the loop and you're leaving a little bit behind, and then it's getting diluted into your rinse, and then it's carrying over to your next blank, it can give you some carryover. So clean and replace your loop. If you're still having issues, again, bypass your standard addition system. And then if you're still seeing issues, clean or replace the transfer tubing that takes the sample from the autosampler to the concentrator. Okay, so now that we've discussed how to troubleshoot, how to find the root cause of our contamination and how to correct it, now let's turn our eye toward the future and how do we prevent these things from reoccurring. First and foremost, make sure that you maintain proper methods. So before making any method changes, ask yourself, why am I making this change and what kind of effect could it potentially have on my analysis, in addition to the positive change that you're hoping to affect. Make sure you retain good records of any changes that are made and why they're made, with especially paying attention to when you made the change specifically. So if you see a problem crop up, you can then tie that back to the time where the change was made and say, yes, this run occurred after the change versus this clean run that occurred before the change. Always make sure you keep a copy of a known good method that you can revert back to as a troubleshooting tool. And then if it's not broke, don't fix it. If your methods work perfectly fine, make sure that your changes are being done for a really valid reason. Don't simply switch columns because you read a different application note that used a different column and you thought you liked it better, or you thought it might improve things. If your system's working really well and you're happy with it, then leave it be. Looking at regular preventative maintenance, on the GC side of things, make sure that you're doing regular inlet maintenance, clipping your columns, making sure that you're cleaning your detectors and tuning them on a regular basis. A special attention should be paid to the column. How many of you out there, show of hands, know how old your column is, know the last time you replaced it, and have a good idea of when you'd like to replace it based on past experience? If you're anything like me, you probably don't know that information. But it's important to know. You really should know where your column is in its lifespan and what kind of issues you'll start to see that suggest it should be replaced. And if you wait too long to replace your column and you start to have these types of problems arise, you can waste valuable time on troubleshooting when in reality it's that your column is old and it's exhausted and you could account for that. Similar on the autosampler side of your systems, making sure that you're cleaning and replacing syringes, solvents, and all of your other consumables on a regular basis. Don't simply wait until they run out regardless of how they look. Don't wait until the syringe is so worn out that it stops transferring the proper volume, things like that. Analytical traps, it's the same as columns. Make sure that you understand the age and the life expectancy that you have with your samples on those traps and replace them on a regular basis before problems occur. In the case of purge and trap concentrators, it can help to track your pressures. So if you have a really consistent purge pressure, for instance, 6 psi over dozens upon dozens of samples, and then suddenly over 2 or 3 samples that rises to 15 or 20, that's a sign that you need to replace that trap. Okay, with your consumables, make sure that you're purchasing all of your consumables from reputable manufacturers. Make sure that you're refreshing your standards and solvents on a regular basis to avoid contamination in the first place. And then make sure that you're using good practice when cleaning all of the glassware in the lab, that you don't introduce problems that don't need to be there in the first place. Okay, and then last but not least, know your samples. Consider pre-screening for your purge and trap samples. So catch those really high samples before you run them through your system and contaminate it. When you have difficult matrices that might leave residues in the sparger, consider an in-vial purge. You keep all that mess in the vial, you don't transfer it to the sparger and then contaminate your liquid pathway. Consider Headspace when possible, especially in place of liquid injections to prevent column fouling, or even in place of purge and trap if possible at high concentration samples to avoid contamination of your purge and trap system. And then increase your maintenance frequency if it's necessary for the types of samples you run. If you run really dirty, nasty samples, you'll have to clean your system up more frequently. Okay. As always, we're here for you. So if you have troubles and you're struggling to figure out where your contamination is coming from, reach out to us. We're more than happy to help. Here's our tech support phone number, and then you can reach our international tech through email, as well as our domestic tech support team through email. You can go to our website, www.teledyne.tekmar.com, and you can always email me directly. I'm more than happy to help with any issues you might have. With that, I'll open up for questions.